In this video, I want to discuss perceptrons, and the reason that we're going to be talking about perceptrons before we talk about neural networks is, well, neural networks are composed of many different, many neurons, and so perceptrons are kind of like they were the very first kind of neural network in the sense that they were really just a single neuron. And so it kind of makes sense to discuss first the component, the part, before we talk about the whole, which is neural networks and multilayer perceptrons. So first we're going to take a second to discuss perceptrons. And to kind of discuss this, we have to discuss a little bit about supervised learning and classification in particular. So suppose that I suppose that I was trying to build some kind of app that can detect the difference between dogs and cats. And so what I'm building is a classifier. When I give it some new data about a new example of a new animal, and I want to figure out whether it's a dog or a cat, I collect some features. In this case, the two features that I'm using are mass or weight and height. And so based on this information, I went out and measured this information from a ton of different dogs and cats, and I've plotted it on this chart here. And now the idea is I want to find some way to separate these two different kind of categories. And so when I give it a new example, I should be able to figure out, based on where it's plotted in this plane, I should be able to figure out whether it's a dog or a cat. That's the goal. So let us see what the result is. So I think it's kind of helpful to see what the output of the perceptron is before we discuss it, so you can kind of keep this in mind to see how all the stuff that we're doing about learning about perceptrons will eventually produce a result like this. And so it turns out that, hey, I can draw a line that separates these two different kind of classes, and if it falls, the idea is if it falls on one side of the line, then I know that it's a dog, and if it falls on the other side of the line, then I know that this is a cat. And so I've drawn the line. This is also called the decision boundary, because it's based on this boundary you make a decision whether it's a dog or a cat. And so the equation of this line is what I've shown here at the bottom, like right over here. And you can see it's W1 times X1 plus W2 times X2 plus B. And so what is X1 and X2? Well, X1 and X2 so X1 represents the mass and X2 represents the height. And then this B is just a bias term to kind of offset it from the origin. If we didn't have a bias term, then our line could only go through the origin, which wouldn't really give it as much expressive power as if we had a bias. And so this decision boundary is W1 to X1 plus W2 X2 plus B equals 0. This is the equation of a line, right? So based on this line, whether we can take some new input, get there some new mass and some new height, so a new example, and suppose that I've already trained my perceptron, so I already know what the values of W1, W2, and B are. Those are called the trainable parameters, in which case we want to give our perceptron an example so it can learn what those values are. And once it knows what these values are, then we can give it a new example and use those values to compute on which side of this decision boundary is my new example, and from there I can make a decision. And of course, we can actually rewrite this in vector form, but we're going to kind of skip that. So supervised learning, as I mentioned, is where we present we have already examples that we've collected, and we know what their ground truth labels are, and we call the ground truth is the true example of here's some input, and here is a particular what the true example of this is, and I showed you that in the previous slide, right? So we have examples here, and we know what the actual truth is, whether they're a dog or a cat. So we present pairs of these data and the correct answers to our classifier in hopes that it will learn some way to separate all of the different classes. And so that way when we give it new data, then it can categorize it in the appropriate classes. And so kind of one thing to note is that the data in the example that we're going to be using, the data is fairly low dimensional in the sense that there aren't that many features. In fact, we're only using two features, right? Mass and height. But in reality, if you're doing something like data science, you actually have many, many, many features. And so X represents the vector of all of your features. And for our classifier, X is a vector where the first component is mass and the second component is height. And again, if you're doing like things like with data science, with much more information, like a classic example is predicting the price of houses based on maybe like how many bedrooms it has, how many bathrooms it has, square footage, and whatnot. You would take all that information, all those features, and then put them into a single vector and call that your input. And so in our case, we just have two features. We just have mass and we have height for our classifier. And now as for our output, well, we only have two classes, and so we're going to use binary output. And that's kind of one important thing to note of the perceptron that I'll reiterate towards the end, is that perceptrons are only useful for binary classification. In other words, you only have two classes that you're trying to separate. It doesn't generalize straightforwardly to more classes. There are other kind of adaptations that can, of course, many classifiers, like neural networks, for example, can do multi-class classification, but perceptrons are kind of limited in the sense that they can only do one kind of classification, binary classification. Okay, that is supervised learning. So here's a little bit more information on the perceptron. So they were like the first kinds of neural networks, in the sense that they were only a single neuron. And it turns out they weren't actually developed by a computer scientist per se. They're actually invented by a psychologist named Frank Rosenblatt. This is, again, many decades ago. And he was a psychologist, and he actually modeled these after biological neurons in our brain. And these were actually very loosely modeled, because at the time we didn't know that much information about the brain to begin with. Now we know much more information, and these are like really, really approximate models. And actually, you can go and look at a picture of the biological neuron and see, make the comparison yourself. But anyway, let's actually take a look at an example of what a perceptron would look like. So here is what it kind of looks like, and so you notice that we have some inputs. We have an input vector, actually, and I just listed all the components. And for each component, we have an associated weight. And so we have as many weights as we have components. And then we multiply each component of my input with its corresponding weight, and then I just sum them all up together. I add up my bias, and that produces, I'm going to call that value Z. And then I apply this thing called an activation function, and that gets my thing A out. And this is actually similar to the, like I mentioned, biological neurons in a sense, because the inputs represent all of the inputs going into a neuron, and the weights are the weights of the neuron. And what's happening inside a biological neuron, roughly, is that it takes all of its input and kind of combines it together, and then the neuron either produces a single output, it fires, or it doesn't do anything. And so this is where Rosenblatt kind of devised the idea of the perceptron. And so this is basically the structure of perceptron, what it looks like in the most general form. But there's kind of maybe one question you're asking is, what's this magic activation function? If you look at this, the weights can really be anything. So the question is, if your output is supposed to be 0 or 1, but Z can be any value, you need to come up with some function that takes any kind of input and produces only 2 outputs. And hey, we can do that. It's called the step function or threshold function. And essentially, you just look at the input, and if the input is greater than or equal to 0, you produce 1. If it's less than 0, you produce 0. And so here's a plot of the function on the left. And so we can apply this activation function, and then you can take pretty much any input from any domain and then condense it down into just a binary class. And so the output tells me what class, so the output of the perceptron here tells me what class label I should assign to that particular input. Okay, so I'm going to stop right here And to make things clear, actually, in the next video, we're actually going to go through an example by hand of how would we select the values for a perceptron. And so this will hopefully give you kind of a better idea of how these things actually work. So I'm going to stop the video right here, and in the next video we're going to discuss how we're going to kind of do an example of Perceptron by hand.